Hello, everyone. Thank you very much for coming to the first ITC Colloquium of the new semester. This week we'll be hearing from Dr. Javier Vian, who is from MIT. Before, he received his PhD in Explainable AI from the University of Cincinnati, and after that has been a postdoc at MIT for the last 3.5 years. And he is working on a cross-section between explainable AI and astronomy, and how we can use AI and apply it to astronomy and all the things that we are interested in here. So everyone, here we are for Javier Vian.
Hello, nice to see you, everybody. I'm very excited to tell you about this work. Before that, I'm gonna put a timer so I don't forget to keep an eye on that. Okay, I'm gonna be telling you about a very interesting field within AI that I'm very passionate about. It's explainable AI. It's a type of AI that, as I'll tell you later, explains the reasoning of the model and allows you to do so much more with it, okay? And then I'll be talking about two main use cases. The first one, the real-time microlensing detection, and the second one, the stellar clusters population studies, right? And how we can leverage XAI for that. All right, just an index of the presentation. Before we start getting into the use cases, the first topic is, what is explainable AI? How does it work? What are the types of that? And yeah, how can we understand the model, a trained model reasoning, right? And then later on, we'll talk about the two use cases, as I was telling you. The first one will be focused on validating predictions that are done using AI. And the second one will be focused on extracting expert knowledge with explainable AI. So two different applications of explainability in artificial intelligence. All right, so before we start talking about explainability, what is really AI? Just as a reminder, the way I like to see it is you have an input, right? Something comes in and something comes out. And you have a model in the middle. And this model is trained based on some data that we have, right? So if you have some training, if you have some parameters that have been updated in there, then we consider that some AI, right? Some form of AI. You can think of it as a linear function, right? As a linear fit. Well, to me, that is a model of artificial intelligence, very simplistic, very, the simplest probably out there. But you have trained model, a parameter or a set of parameters based on some data, right? Now, what is the difference between regular AI and explainable AI? The main difference is that you not only get the output that you're looking for, you also get an explanation, right? So what was the train of thought of the model? How can we use that? And that is very, for obvious reasons, right? We don't want to, depend on these models and just get outputs and trust them blindly. You want to understand them. But I've seen that it's very useful in astronomy for various reasons. So XAI allows you to do, within astronomy, two main things that I think are very important, others as well, but I'm going to be talking about these two. The first one is validation of AI predictions. Now, checking if the reasoning of the model was okay helps us decide whether, before we can allocate time of valuable telescope resources, whether that is okay or not. That is the first thing. So you have a pipeline that predicts something, and then you can validate with XAI. The second one that I'm most passionate about as well is doing science. Can we extract new theories from the models that have learned from the data, right? So, well, new ideas that we didn't thought of. And these are exactly the two use cases I'm gonna tell you about. The first one is validation of microlensing detection with AI, and doing so autonomously because, obviously, it's really easy to just predict visually if this is a microlensing or not, as a human, if you are trained properly, but that would be repeating sort of the decision making as opposed to validating a prediction of a model. And then you have doing science, which is the case that I'll be talking about today, is understanding whether, what are the star cluster aging physics in space, right? So that's the sort of application. Now, before we get into those, two types of explainable AI technologies that we have out there, I like to classify them as bottom-up approaches and top-down, right? Bottom-up, it means that you have, from the very beginning, a pipeline, an algorithm that is already explainable, that you can understand, because the model itself is transparent, right? For example, a linear regression. That's very clear. It's an analytical formula. You have the parameters, easy. decision trees, genetic fuzzy systems. There's others, neuro fuzzy systems. Fuzzy logic has been leading some of the AI, explainable AI world, in my opinion, that are for bottom-up approaches, right? And then I'll be talking later in the luncheon, and I have another slide, just one more, about CFIDER, which is a pipeline that I've worked on, and my team as well, during the PhD. So I'll tell you a bit about that as well. And then you have the top-down approaches, which are, well, you start from a pre-trained deep learning model, and then you sort of do the reverse engineering to understand what's happening inside. It's a black box, so it's already a black box, but now you try to understand what's inside. You look at the weights, you look at the contributions, and so on. I'll give you examples of both. So one example that is a little more complex than a linear regression of a bottom-up approach is the so-called CFIDER that I worked on, that basically is trying to replace the neuron of a neural network by something more complex than an aggregation of weights and then an activation function. So in a way, you're looking at a configuration of 2 inputs, 2 outputs problem, and then there's 3 layers in the model. And just to touch a little bit on that, in every neuron you have a complex mapping between the inputs and the output. And you can extract from there some sort of like simple function as well, because it's an aggregation of like simple functions that together they make a complex one. Anyway, if you want to learn more about it, you can come to the luncheon later. An example of a top-down explainable AI approach is integrated gradients, okay? And this is one of my favorites. It's basically like calculating the gradient, right, of the model. You have a neural network, and you look at the derivative of the output with respect to the input, but you do so in an integrated way, right? So you start from no input at all, and you go all the way to the input that you're looking at. So you're smoothly increasing, the gradient before you get to the one that you want to calculate. And that is a way of like smoothing out the possibilities that you can get. And you use that coefficient alpha to go from the base input, which could be a null matrix or a null input, to all the way to the one that you're looking at. Anyway, if you simplify it, you have to multiply times the fed input. But if you simplify it, you end up having, with the Riemann sums, you have a simplification of this formulation. So an example, right? Imagine you're classifying cats and dogs. You have an image. You want to see if it's a cat or a dog. And now we have a pipeline. It's predicting well. But now, how can we see how much information is contributing to that prediction? Well, you start from the null matrix, right? And then you go all the way to your original image. And at every point, you calculate the gradient. And when you aggregate all those, you end up having the integrated gradients function, right? Well, the mapping. So for example, the POI is contributing a lot to classifying that as the cat and so on. Anyway, we'll use that technology for the 2 use cases that I told you. So how XAI can help us validate microlensing predictions? Well, we worked on this pipeline that is called LensNet, together with Jennifer, who's also in the audience, and Andrew. And we basically try to predict whether there's a real-time a microlensing event happening or not, right? And we used a pipeline called LensNet for that, and I'll also tell you about how to validate those predictions, right? Before we get into that, of course, I have to explain you how the pipeline works and what is the whole point, right? Which also has an astronomy application, so it's very interesting. This is a microlensing event, right? You have a background star, and then you have a foreground object, which could be a star, could be a planet, and passes right in front of the background one. And of course, the light of the one that is on the back, it's augmented, it's magnified, as the one that is in the front passes by. Now, this is a very powerful tool to detect, for example, exoplanets. Why? Because, well, if you have exoplanet orbiting around the foreground star, the lens star, as we call it, it's going to generate a secondary sort of spike, or, well, it's going to modify the Pasinsky curves, right, as we call them, of the transit, sort of. So it's a very useful way of detecting exoplanets, because once you know there's a microlensing event happening, you can then trigger other telescopes to point at that source, and then obtain from there whether there's a microlensing, an exoplanet or not, right? So we worked on the Korean Microlensing Telescope Network. This has 3 telescopes, CTIO, SAO, and SSO, located in Chile, South Africa, and Australia. And, well, here are the specs of the telescopes. But the whole point is to be looking at the same region of the sky all the time. And that allows you to monitor whether there's a potential microlensing. OK, so a summary of how do we detect, initially, how do we alert the people there's something going on in real time? Well, you have the 3 fluxes, right? The 3 curves of the 3 telescopes, right? Each of them has a color in here. And then at a certain point, right, what we call TCAT here, in the horizontal axis you have time, in the vertical you have the flux. You trigger the pipeline, and it predicts that there's a rising alert. Now that is a phenomenon that is, the flux is increasing with respect to a baseline that is horizontal. And at that point, we can tell that something's going on there, right? But we are not sure whether it is a real microlensing or not. So there's a decision that comes in, right? So you first have the alert finder system, which is exactly what I told you. And then you have, you try to incorporate a human to classify whether this is a real microlensing or not. Now, when the human looks at the curve, first thing, it has to be a trained human. It's a very complex decision because there's a lot of wiggles that can happen there. It's not an easy decision to make. You need to understand a lot of, you need to at least have that notion that is, if it's sinusoidal or if the pattern is in a certain way. So you can classify directly if this is a no candidate, if you reject it. But you could also have it as a potential candidate. And later on, when you look at the difference image, you can reject it finally. And that would be the case of the maybes category. So if you first think that it could look like a potential, but then you reject it because of the difference image, that is a maybe category. And if it is a real microlensing, that would be a yes category. So we have these 3 categories that we are interested in sort of automating for the predictions. And that's what we want to replace with LensNet, OK? And that's exactly what we did. But before we get in there, just to show you a little bit about the complexity, I'll show you a couple examples. The first one, this is a real microlensing. OK, you have on the left the 3 fluxes. Well, that's the entire event, right? And then on the bottom, you have the 4 previous seasons of that particular star. On the right, you have 2 plots on the top that are like this moment where the alert finder was triggered, the increasing event, and then the comparison with the previous years. And that's what we have. We have the information from the right to make the decision in real time whether this is a microlensing or not. We don't have the entire event. That's very important because it's much easier, right? Once it's finished, it would be easier to classify it. This is not a microlensing event, for example. So someone theoretically could look at it and could say that it could be, but I mean, there's reasons why it's not, but it's not an easy thing to do. It's not just like sort of like a Gaussian-shaped curve that could be a microlensing. The takeaway is that it's not easy to do visually, right? And for that matter, we trained a neural network to do it. So before we trained it, we decided to augment the data in a certain way. We took these fluxes of every curve, right, of every telescope, and we cropped it from the right and from the left to sort of generate more data, right? And this way, we can increase it by a certain fold, the entire data set, which allows us to then train it for longer, better, and then the model, it's resilient to those variations as well. Because there's instances where we have less information at the beginning of the season, for example. You don't have that much information available. And then there's cases where you have a lot of information at the end of the season. This is sort of how the pipeline looks. Well, the first pipeline that we worked on, there's an updated one that I'll tell you a little bit about it. You can think of it as 3 blocks, right? The top block is the CTIO data. You have the flux. You have the flux error, different features that we considered initially. And then the air mass and so on. And then you process each of those features with certain functions. So relativization, outlier removal, you do some fitting, some standardization, some padding, and so on. Padding is a very interesting concept in AI. You basically have here non-fixed length variables. So like every input could be different lengths. And you want to standardize them in a way, right? So you put a bunch of zeros at the beginning or at the end. You could do it with other values, but that's the idea of like standardizing the length of all the different inputs. And then you process that with a network. In this case, we used a recurrent network for that matter, for that nature of like different lengths in the inputs. So we chose an LSTM that allows you, it's a long short-term memory. It allows you to preserve information from the recent data, but also from very little, past data. So from the very beginning of the season, for example, and sort of keep the ones that matter, right? Features, so for example, if there's a spike at a certain point, then you're gonna decrease the probability or the confidence on classifying this as a microlensing if that was very early on before the rising event, right? And this is a very common plot in AI that it's called unrolling the LSTM. You're showing what's happening at every state, and you use that recurrently, so you get a final prediction by the end you have visited the entire series. And then you use the same approach on the other two telescopes. We merge them together. We use those embeddings with a final neural network that makes the classification. Okay, I know I'm not talking about explainable AI, but before I can talk about it, I wanted to give an overview of how this works, and I feel like it's going to help you understand some of the concepts that we'll talk about later. So how do we tell if the model is doing good or not? Well, this is a very common plot as well in computer science. You're looking at, on the left, you have the two-class classification problem, right? So classifying the yes categories versus the no's and the maybes. We put them together as a single category. And you have on the horizontal axis the epochs, right? As you're learning. Learning in AI happens gradually. You don't learn right away, just like a student, right? You don't happen to learn everything the first day of class. You have to go for the whole year, and after those 365 days, you know now the whole course, right? So those, we call them epochs. So it's slices of time where we train the model gradually, just like the integrated gradients concepts. We want to do things gradually, smoothly, so we don't do it abruptly, because otherwise you bias the entire learning. So horizontal axis epochs, vertical axis the binary accuracy in this case, or the accuracy of the model, right? And you have two different sets, the training data set and the validation set. The training is the one that you train on, the one that you're looking at. The validation one is the one you keep aside for the model to keep evaluating things as you're learning, just to make sure that you're going in the right way. And both are increasing. Eventually, validation gets horizontal, so we stop there. And then you have on the right the three-class classification problem. Anyway, just an example. Yes?
Why doesn't it start from half? Because that's a random chance of getting it right or wrong.
Sorry, let me go back.
You start from 40%, and, or actually 0 at 0. I would expect it to be
Good point. It should start from 50, right?
Yeah.
But it's not. Why? Because you initialize randomly the network. You choose random parameters. I mean, in an ideal case, imagine you don't have any input at all, and you're training based on nothing. You could converge into 50% because you're guessing at some point or looking at the average or whatever. But you initialize the weights of the model randomly. Think of it as a linear function, and you choose the parameters in a random way. And you are optimizing slowly, but initially, since they were wrong, they could have been completely wrong, right? So it's not a good guess. That would be a good guess, right? It needs to go up before. But it's somewhere there. If you look at the three-class classification problem, it's starting around 33%, which is around the probability that you would get there. Anyway, another interesting plot that, well, maybe it's a little too much for this talk, but I wanted to tell you a little bit about it because I think it's very important and underestimated these days in AI. Robustness, right? Resilience, and this has to do with many other things in LLMs with hallucinations and things like that. But you want to make sure that the model is doing okay, even in very extreme conditions, right? So what we did here is we took the alert, right? Not the entire event or the entire Gaussian sort of function, right, of the microlensing. We took only till the point that we have available data, right? And then we started removing part of that and see how the model performs even with limited amount of data. There's no way the pipeline would work in any of these conditions because obviously we would only use it for the available data that we have, nothing less, right? But just to understand what's happening, I thought it was a good idea to show you this, right? On the horizontal axis of each of these plots, you have the percentage of how much of this alert you're showing to the pipeline. And the vertical axis is the performance, right, of each of the classes. You have different colors. Each color is representing a category. You have the no category, and you have the yes category on the top left. Let's focus on that one because I think it's the easiest to understand. So the idea here is that when you have less data available, what is the performance of the model? And you see that the model is biased towards having better performance on the yes category. Actually, it starts increasing when there's now data available. The model tends to predict that it's a yes, just to be conservative. I found that better than the other case, right? Because if there's no data available, we don't want to forget about any potential microlensing event. It would require further data till we can evaluate it better. But that's the point of these plots, right? It's trying to show how does it behave as you're increasing that amount of information. Another interesting plot that is not very popular in the papers, but I like it more personally. It's similar to, for any of those that know about AI, ROC, receiver operator curves, right? Where you want to assess the performance of the model. So basically, you have a model, and you predict an output, right? What is the output here? Is the probability of being a microlensing event or not? So from 0 to 1. And you have to put a threshold at some point, right? Because it's a classification. It's or yes or no. But if you have an output that is continuous, where do you put the threshold? Someone could think of 0.5, for example, 50%. So if you are above 50%, that's a yes. If you're below, that's a no. But it's better to tune for that parameter. It's a very useful parameter that you can tune for at the very end after the model has trained, just to gain some extra percentage in the performance. So in the horizontal axis, you have the threshold of this model, right? Of these, the output. So if you put like the threshold at 0.0001, for example, any output that you predict that is below that number is going to be classified as a yes. So your performance in the yes category is going to be 100%. You're going to be great at that. But you're never classifying a no. All the instances are going to be classified as a potential microlensing event. So, of course, that is the curve that we look at, the 100% accuracy in the category of the yes, right? That's the vertical dimension is the accuracy. And as you increase that threshold, you're going to go all the way till 0% accuracy in the yes category, because obviously if you only want to classify the yeses that are above 99%, 0.9, and so on, it's going to be very difficult, right? When you take the average of those two curves, you can do the same for the other category, you obtain the curve that is in the middle, and that's the one to optimize, right? You want to look for the performance that has the highest peak in that curve. So it turns out that it's not 0.5 as usual. In this case, we know that it was already biased because of the robustness analysis that I showed you before, that it was biased towards the yes category, so you have to make it a little smaller, the threshold in this case. 0.45 was the right one, around that. Anyway, LensNet was deployed. We are evaluating around, a lot of stars a day. I don't know if 60,000, Jennifer, is it around that? Maybe less, maybe, I don't know. Depends on the day, right? Depends on the day. But it's definitely more than 1,000 stars per day. And it's, it reduces time by the humans. They have to take every day, there's a person that spends 2 hours looking at the screen, classifying these events manually. So this helps us make faster predictions and so on. So many other reasons for us to leverage this technology. And we have updated LensNet now. We're looking at a convolutional architecture as opposed to a recurrent one. We removed some of the features, and we compressed the data. We are looking at encoding the time in a certain way. Still processing things as a branched architecture, right? You see the plot on the bottom left. You remember that one already. You can see that we're getting very good accuracy now. Still could be improved, and we're integrating now information from the previous years. We believe that is a very important information to take into consideration. So for example, these are 2 cases that are not a microlensing event. So these are no categories. And on the first column, you have the information of the previous years of that star. And on the right, you have the information of the 3 telescopes of that star, right? You could think that there was like some increasing there happening. I mean, there's definitely some like curve underlying those patterns, especially in the bottom one. But if you look at the previous year, then you realize this star is doing something weird. So I'm going to reduce the confidence on the prediction of this on this probability, right? Anyway, that is manually done. But now, can we use explainable AI to trust these predictions, right? And that is what I wanted to get to. Now, can we use integrated gradients, right, to understand the reasoning of the model? We can, for sure. And this is exactly what I'll be telling you about. So on the top panel, you have the flux, right? The 3 telescopes that we're looking at. The rising event is on the very end, right? That's the alerted region, right? But we have information about the entire series. So the model, now when we ask the question of, tell me about how much information is contributing, how much every input is contributing to the output, you get the panel that is in the middle. And that is the integrated gradient, right? You see a value that is positive and a value that is negative. If it is positive, it's contributing to higher probability of microlensing. If it is negative, it's contributing to lower probability of microlensing. It cannot be less than 0 or higher than 1, so in some constraints. So it has to be balanced in a way. So if there's a very, very strong peak downwards, there has to be some other upwards that counterbalances that a little bit. But the average would tell you where is the decision going, in what way. So if you smooth those integrated gradients, like the bottom plot before, after that, you obtain that in the bottom area, in the sort of like first Gaussian or first mountain that appears there, the pipeline is thinking that this is negatively impacting the model. So the fact that the presence of this sinusoidal behavior is telling us that this is not a microlensing event, and that's why the integrated gradient technology told us, or algorithm told us, that this is not a microlensing because of this reason, because of the presence of this sinusoidal.
What is the horizontal axis?
Yeah, 0 contribution. That is not contributing at all to the prediction.
No, horizontal axis, time.
Yeah. The horizontal, sorry. I thought, yeah. The horizontal axis in this case is the time, right? So you can think of it as, it's the same for the 3. So the time in the top, and then the flux in the vertical axis, so every instance, every observation.
What are the units?
What are the units?
Multiple years?
Yes, it's Julian date.
Julian date, okay.
Yeah, well, relative, because we relativize it so that the first observation of the year is at 0. Well, in a way, for this pipeline, right, for the plot.
So this is going over multiple years?
No, this is just a single season.
So the numbers are not individual days?
They are not?
Aren't those individual points?
Yes, sorry.
Yeah.
These are individual instances, exactly. No, so it's index of the observations. Yes, you caught a mistake. It's not time. Well, I mean, it's a proxy or a index.
Because microlensing cannot last so long.
Exactly. Sorry. I was focused on the time scale, and you're right. But no, it's the index of the but it's it's compared to time. Anyway, let me go to another example. This is a microlensing event, so it was classified correctly by LensNet. Again, in this case, there's no sinusoidal pattern or anything, but there is an increasing event later, and the model is actually telling us in the bottom plot that this is the area that is mostly contributing towards predicting that positive microlensing, because it's higher the contribution than the average of the entire set. Definitely everything's contributing. You can see that the stability contributes positively to classifying it as a microlensing, so that helps. But also the model focuses mainly on the rising region. So anyway, that's a way of validating. All right, let's go to, I thought that was a good way of telling you, well, explainable AI is helpful. If we could automate it, if we want to automate it, to validate predictions, we could use these sort of like technologies to do that, right? So not just deploying the AI pipeline to make the predictions, but also deploying sort of the explainability reasoning as well. Okay, explainable AI to learn about star clusters. Now, the question here is how much age-related information is encoded in each region, right, of the image. So the model in this case is going to be taking each of these images, right, individually, right? These are different star clusters, and then predicting whether this is, if this is, what is the age of this star cluster? It's a regression problem as opposed to the previous one that was a classification problem. Although every classification problem is really a regression problem behind the scenes. But can we predict what is the age of each of these? So yes, we can, and the way to do it is taking the image training a neural network model and predicting the age. But that is not the ultimate goal of the project, is understanding how much the environment, for example, is contributing to that final age prediction. Things like that, right? So now you can extract the information of the reasoning of the model, right, with explainable AI to get some sort of knowledge. We're going to study two cases, the 5 filters case of, HST data, and then the white stacked image, basically the mean filter, the mean average of the mean of those 5 filters as potential inputs, right? Okay, so for the case of the 5 filters, again, you remember this plot, horizontal axis epochs, vertical axis, in this case, is not the accuracy, it's the opposite, is the error, right, mean squared error. And as you are increasing the epochs, you should decrease the error. Eventually, validation is stable. And on the right, you have another very typical plot in AI. There's 2 plots, but the one on the top, horizontal axis is the truth value, the truth age, and the vertical axis is the predicted age. You want those 2 to match. You want that to be diagonal in an ideal world, but obviously, there's some scatter. This is for the test data. The test data, I mentioned training, data that we use for training, validation, data that we keep aside as we're training to verify that everything's going right, and then test data that we keep until the very end, after the training has finished, that we evaluate things on. So this is scatter. It's definitely diagonal. It's showing that there's some learning happening, and it's good. The bottom shows the errors on the vertical axis, and the horizontal, it's still the truth. There's definitely some degeneracies in the extreme ages. So very young star clusters, very old star clusters, but those are, the truth value we obtained by fitting the SED, and we know there's some degeneracies especially in the very extreme ages. So that's also another added challenge for this data set, that the truth is not really truth, it's not ground truth. There's some noise there. We're working on some pipelines to remove that noise of the degeneracies that we obtain from the SED fitting by looking at nearby predictions and so on. Anyway, so those degeneracies, we decided to remove them, at least for the extreme ages, just to see how the model was doing. So on the left, you see the case with extreme ages, the full sample, right? And on the right, you see the case without these extreme ages. So anything below the units of that are in age is log 10. So anything below 10 to the power 7 years, and anything above 9.5, 10 to the power 9.5 years.
Did you say how you were getting the true ages?
Yes, we do SED fitting on the star clusters.
Okay, so it's really the AI
It's
of the
photometry,
SED.
yeah.
They're not really ages. That's okay.
Yeah, well, it's a proxy of that, I guess.
Sure,
Yeah.
okay.
But I'm not super knowledgeable on the part of that. But maybe we can keep talking about that later. Because I know that they use the different, they use a photometric aperture for that of 12 pixels. What was the raw truth?
It's actually 0, so that's fine. Okay.
Okay, well, but yeah, the bottom line of this is the model performs differently when you remove the extremes. And we can assess that with these plots. Anyway. Yes. Yes,
So
yes.
it's missing something.
I mean, the average is still.
I would say there is a slope.
It's a really
Probably.
weird color table, because the yellow is a very low number of counts, and that's what your eye is seeing, right?
Well, I see a slope here.
Right, but look only at the red and the blue, it's better.
Oh, okay.
See, because it's a very weird.
Oh, right.
Yeah,
color
the
choice.
color map I didn't chose the best, but yeah, the blue one is the highest. So the yellow is like the smallest. I would say. Yeah, true.
Okay.
But I look at this, I could have fitted a straight line, right, to this data. Shouldn't the AI do better?
What do you mean? What do you mean fit in a straight line?
If you gave me predicted and true values, I can make up what you plotted in the left, and I can fit a straight line, which will
Correct it a little bit. We've tried. That's a common post-processing tool that some people try, but the model is already capable of it's a universal approximator. It should get to the best answer. When you do that, you have worse performance in the entire collective. So if you fit if you apply a fitted line in the top left plot, for example, you have worse performance than if you keep this one.
Okay,
We
so
try
you're
that.
saying it's doing better, because an old-fashioned astronomer would just fit a straight line and say, yeah, I've got a way of predicting.
Well, I mean, the input here is not the horizontal axis. The input is the image. What the model is looking at is the image. This is the performance plot. So in the
Okay, sorry.
No,
I
but
got that.
I thought you
got
were
that.
asking how can we correct and make it even better based on the prediction of the model and so on.
Okay,
Yeah.
fine, thank you.
No worries.
So are you going to tell us later what the model used to predict the ages?
Yes. Sorry.
It's the spectrum.
Maybe I missed that, but these are the two inputs of the model. So there's two cases that we study. In this one that I was showing you is the 5 filters. So the model is taking those as the inputs, the image, and nothing else.
So wait a second, so the SED has 5 points, just
Yes.
5 colors
Yeah.
for each star?
We aggregate we could have as many as we wanted.
I know, but in this example, I mean, you said SED, right? And so that's how you're getting the ages, right?
Yeah,
And-
that's.
Well,
It really has
he's
5
also
points.
using the image somehow. Are you using the image or the colors?
No, the image.
Images are
Andrew, you
five
wanted to
different
say something, right?
So the ground truth quote-unquote age is coming from the FANG's collaboration, and they're doing SED fitting with those 5 colors.
Right.
And then they're going and post-processing it a little bit with their own tweaks here or there, but it's almost all determined by those 5 filters.
Got it.
Yeah, but what about the image? Is the image important or not?
No.
So the image is irrelevant.
Aperture
It's-
photometry on
So-
5.
For the photometry, they do
For the
they-
ground truth, they throw out everything outside of their photometric aperture.
Exactly. They
What
only
happens
take the
is-
photometry.
Okay, so we don't care about the
Is
image.
now
It's just-
recover that using the full image or subsets of that image.
You do
Exactly.
probably because there's a photometry step where they take an aperture and decide how big the cluster is.
Sure, but
That-
the
that's the only reason
distribution
you
of
care.
light within that
No.
aperture doesn't matter.
Exactly.
Yeah, okay.
Right?
For the initial ground truth ages, yes, that's correct.
For the initial ground truth. But now what we are trying to demonstrate is if we take as input the entire image, can we predict that age without that information of the SED? That's sort of the tricky part because remember, what is the whole point of this? We want to see how much information is contributing each region of the image. So like, for example, is the environment contributing to the age? We believe it is. So that is the idea, right? So now, a little more about the input. How can we find the contribution of the environment to that final prediction? Well, you could take the entire image, right, as input as we have it, but you can also take just the environment and put an occlusion in the center. The star cluster, by the way, I didn't mention, it's exactly at the center of the image, right? And it's roughly around 12 pixels maximum. It doesn't go past that much more. But if you take a radius, for example, like that one, you're covering pretty much all the star clusters of all the data set that you have. So if you train a pipeline exactly only on this environment, and you have a valid performance, that means that there's relevant information that the model has picked up to predict that age, right? And then you can do the opposite, right? Just focus on the star cluster center itself and then predict the age from there. Obviously, well, if that's the most relevant information for the age, it should do a better job, right? So anyway, so this is what we learned, right? All right, let's go this step by step. On the very bottom, we have the first case, right? 5 HST filters. Here we have the color of the filters, or we call that color, the morphology, right, of the star cluster, and you also have the environment information. We train this branch convolutional neural network, and we get this performance for the full sample with the extreme ages. When we collapse those 5 into a single stacked white light image, we just have for morphology and environment. We train another CNN set, and we obtain that performance, worse than the first. Then we have the 24 pixel radius diameter, 24 pixel diameter cluster plus near environment, we could say. And then we get another performance. There's an interesting phenomenon that happens here, that when we make the model focus only on the region that matters the most, in this case, you sort of get a little better performance, because in the horizontal axis we have the dex, right? So the lower, the better. It's kind of like when you are asking a student to learn only one chapter and you are examining that student on that chapter, as opposed to teaching the student the whole book and then examining on one chapter. So you focus the network. The case 4, 12 pixels, that's a little higher. And then we go outside 12 pixels diameter for the environment. And you see that, well, it's doing a little worse, yes. When you remove and you go all the way to 24 pixels diameter, you still have a little less. And now, what is the very top case, which is, it's a very important case to compare and to understand this plot, is the baseline prediction. It's a fixed guess. See, we could have guessed the age of the star cluster randomly with predictions, random predictions, and that would give you a much worse DEX that I didn't plot in this table because it was going above the charts. But if we train the most simplistic AI, I lied before because I said it was a linear regression, but no, the most simple AI that you could train for is the mean of the training sample. So you could, what is the mean of the training sample, the mean age of the training sample? Let's say it's 10 to the power 7 years, sorry. So 10 to the power 7 could be the prediction for every instance that we get, and always making the same prediction, a fixed guess. Now, that would get you a baseline performance, a baseline scatter, and it's the very top one. Anything below that has predictive information, right? So if we are making better than a fixed guess based on the training data, there's relevant information present in the data to predict the age, all right? So in this case, we found very interesting that there's useful information encoded in the environment of the star cluster, not in the star cluster itself. And now if you talk to the people that actually know about star clusters, they might tell you, well, there might be some remnants, some information that is relevant for the star cluster and how it evolved and so on. Okay, so now let's do this comparison where I added a couple cases here. The 5 filters with, well, masking the environment and masking the star cluster. And then we have 2 examples, the full sample and the case without extreme ages. It's funny that when we have, I don't know if this works, yes it does. When we have only the environment, right, the case 8, 24 pixels diameter, outside of that there's really nothing, no star cluster that could possibly lead out. And in this case, it's only the cluster morphology. So these 2, they have similar performance, case 8 and case 6, when we are removing the extreme ages. So they sort of contribute around the same. It's high DEX, but still, I think it's less than the fixed guess, so there's predictive power. It makes sense to compare them. And we found that interesting. Again, same behavior here. You have less performance when you focus only on the region that matters, for sure, because there's a lot of information here, and this is the book of the student example that I was telling you before. Okay. Now, you could run this analysis a little farther and start increasing the diameter of this masking, so on and so forth. So on the horizontal axis, you have the number of pixels of the blackout diameter, and there's 2 plots here. The vertical axis of the top is the mean scatter, so the DEX. We are showing training, testing, and validation sets, right? The training, we put it on sort of like that dark color because it doesn't matter as much. But the important ones, because you could train, you could get to 0%. But you only train until there's this stability in the evolution curve that we talked about before. And then you have the validation and test set. As you are removing the first pixels of the image of the center, you're losing the majority of the information because that one has a lot of information. But later on, there's still some relevant data. This is for the 4 cases that we have, right? So on the top, the 5 filters case, the 2, right? The full sample and the case without extreme ages. And on the bottom, the case with the stacked white light image, right? And the same plot, right? Predictive power on the bottom of each plot, by the way. I didn't mention that. But yeah, interesting to see that, well, the sudden loss in here is not that good because it's very close to that, and then it's very horizontal after that. But in here, when we are looking at the full sample, they still have that trend as you are removing more and more. So as you remove more information of the environment, you're losing performance because you're removing more and more anyway. All right. Eventually, you would converge to the mean, by the way.
On this white light image.
This one.
Right. There are no filters, right? It's just one
Just
number,
the average.
one number for each star.
Yeah, that's the prediction. That's what we're trying to predict the
No,
age.
no,
Yes.
what's the data that you're giving it?
The input is an image.
It's an image, right? So you-
112 by 112.
Good, so you get spatial information.
Yes.
And for each pixel, you also get the intensity, how bright it is.
We
Or do
rel-
you remove that?
We relativize it.
Ah, okay.
I didn't mention that, I should have. We normalize it so it's between 0 and 1 every image. So we don't have the relative information across different instances. We impose that extra punishment to the model.
Okay. So really, this is just focusing on the locations?
So you can think of it this way. Well, I didn't mention, but for every point, there's 5 models, 5 convolutional models that we train, the mean, and then the vertical dimension, the scatter. So yeah, one of these models, so one of these points represents 5 models. If you go into one of these models, what you have as input, in this particular case on the bottom left, is the image, 112 by 112, with the masking in the center, and there's at least one value that has a 0 and at least one value that has a 1 within that image,
That's the
and everything
representation.
between. But there's no relative scale.
Okay. And just with that, it can actually,
Perform better than a random guess,
Okay.
which is these horizontal lines,
Okay.
and that's the whole point.
okay.
But thank you for helping. Okay, now we also wanted to check, how it's doing for the near star clusters and the closest star clusters. So we look at the near versus far galaxies, and we double check that the distributions were sort of comparable when we are talking about that. There's a lot of phenomena happening because I'm going to skip to the next one, but the distribution of the near galaxies and the far galaxies, the age of those star clusters. Well, first it's a different number of the number of clusters that we have in each, and then it's a different distribution. There's more degenerate star clusters in the far galaxies than in the. In the data set that we have, I think we have around 20 galaxies, and there's 4 of those that we consider as the closest of the sample, and 5 of those at the very end that are the farthest. And I think it's 18 megaparsecs for the farthest ones, and around 9 megaparsecs for the closest ones.
So that's basically resolution, right?
Yeah, no, I don't know if.
Well,
Yeah.
that's nothing in distance for cosmological distance.
It's small,
They're both-
but for
It's
our
near.
sample.
They're both near.
They are all,
Okay,
The
they're both
resolution is
near.
worse for the far
Good point,
ones.
good point. For our, I missed that part of the knowledge, but for our data sample is our stream, so the data. We're not working with anything past that or with anything closer. So it's within our sample what is close and what is far.
But the pixel size is not scaled by distance, right? So in other words, 12 pixels is a different linear size at
Exactly.
far than the near,
It's
right?
half.
And that's what you're asking about.
Yeah, I mean, you do the fraction of that, and then, so what, 12 pixels, well, the distance of the star cluster, I think it's more or less the same in all the star clusters, but when,
Within one galaxy, but you just said there's near ones and far ones.
Yeah, so if you go back one slide, Javi,
Yeah.
what you can kind of see is that the inflection point changes between the near and the far galaxies, as you would expect, because you're losing all of the light of the cluster at a smaller pixel radius for the more distant galaxies. I think it's easiest to see in that top right image,
Mhm.
although I only see. It's hard for me to distinguish the two, the colors are the same.
well, I can show you a better plot that I have in the paper that we're putting together later, so you can study better. But the idea, the whole point of this was to check, well, is the far galaxy or the closer galaxy doing much worse or much better, or like, is there a similar pattern when we are comparing them? Again, testing only on the test data. But again, we can discuss it later further. So now, let's go back to the explainable AI part. How can we use integrated gradients here to see the reasoning of the model? Now, this is my favorite part of the talk. Can we reverse engineer the reasoning of the model and therefore extract knowledge from there? Turns out we can. So if we look at an image like this on the left, and then we apply the integrated gradients concept, we obtain this pattern. Now, positive and negative values of the integrated gradients, there's 2 things that we can highlight from here. The first one, there's a halo around the main star cluster, blue color halo, well, positive integrated gradient. That positive integrated gradient circle surrounding the main source tells us that the clusters over time grow to spread out. Why? Because the higher is the intensity within those pixels of the halo, or the circle, the more is going to contribute to a higher H, because it's a positive contribution. So the model has been able to pick up a way to explain theory, physics, in some way, right? I didn't know this before we started working on the project, that older stars, they are more diffuminated, sort of. They grow to spread out, right? Second, there's a negative integrated gradient in the center cluster. What does that mean? That the very bright center clusters are very young ones, because they contribute a lot negatively to the H. And the opposite as well. Clusters, over time, they get fainter in the center. So what we learned from this single image is that, there we go, that you could compare it to this, the partial derivative of a 2D Gaussian with respect to the sigma, where the model, the AI, has been able to pick up that sort of surrounding and the bright intensity in the center. And as galaxies evolve, it's like a Gaussian that is getting flatter and more horizontal, but the mass is conserved and sort of like increases on the sides. And I found that a really interesting way of like extracting physics from a model that doesn't know at all about the physics, but has picked that up from the data. More stuff that is interesting is the absence of nearby stars. So for example, a lot of this blue color that the model has been showing in the integrated gradients is telling us that, this absence is contributing to higher ages. So absence of nearby stars contributes to that, making it an older cluster. And the opposite as well. When we have a lot of point sources nearby, presence of nearby sources contributes to younger clusters. And indeed, this is one of the youngest. So I found that very interesting. Anyway, and also I didn't mention, but the occlusions analysis that we had before, it's another way of doing explainable AI in a different way to see how much is contributing every region of the image. Well, conclusions of this talk. I just wanted to show you that explainable AI is a very powerful tool to do various things in astronomy. One thing could be validating predictions of an AI pipeline that is already deployed. But another very interesting thing is, we could quantify or obtain theories or extract actual knowledge from a pre-trained model, in this case, to predict the age of star clusters. Anyway, that's it. If you have any questions, I will be more than happy to take them. Yes?
Thank you. It's awesome. I was wondering if you try to also add CO data. So presumably there's, in the second part, presumably there's a lot of information in the environment and the gas where their clusters, younger clusters will live in a dense environment, older or more intermediate ages will create like this feedback-driven bubbles and things like that. So
we were limited to the data from HST that I was telling you, the FANGS data set. So are you asking?
Yeah, but CO is part of things, so they have like Kalmar maps for all of these galaxies.
We didn't take it into account, but that could be another step forward. We're finishing, about to submit the first paper, the first part, and then we can delve further into other inputs as well, see how much are those contributing to the final age prediction. But there's definitely more things that you could feed into the model and then see how much that is contributing to the output, for sure. Well, yeah.
Yeah, the last example, the Gaussian width, that's very nice. I mean, clean analysis. I was wondering, do you give the algorithm the distance to but you tell it that they're all at the same distance?
They don't know that. The model doesn't know that. It only knows the image itself and the relative scale between 0 and 1 within each image.
Yeah, the reason I'm asking is, you can take the same cluster and move the distance, and it'll look either more compact or more extended.
Good point.
Right? That's not age, that's distance. So how does it break that degeneracy if it doesn't have distance information?
The model has seen a pattern that is able to make those guesses based on the data itself. Maybe, do you have a follow-up answer to that? Or different question. Well, I think it's difficult to tell. Again, I'm not an expert within the field of star clusters. I'm more on the AI part. But it could be anything. It could be that there's some instances that maybe are similar to each other that sort of break that degeneracy apart and finds that correlation and it's able to tell. There's many things that could be.
That's the one you should explore, right?
Okay.
You're saying different distances within the same galaxy?
No, two different
No,
guys.
no.
Yeah,
one
but I
galaxy.
think he's only looking at.
It only changes by a factor of 2, so
Yeah.
we just have learned that if you see big differences, that tells you that it's an age effect. But probably you could just add in the age as a scalar feature to your model, Javi, and then it would do even better.
That's what I would guess.
Yeah.
Yeah.
Well, but if you are
And the
feeding the
gradient
age,
analysis may even tell you
Yeah, that's a really good
how that
idea.
information.
but
is
if you are feeding the age, you're all cheating.
Oh,
sir.
yeah, that's what I meant.
Not the
The
distance,
distance,
yeah,
not
the
the
distance.
Really
Ah, if you are feeding the
Give it
distance.
the distance, yeah.
I knew what you meant.
You look really good with the age.
I mean, but also, I mean, true. We could feed many other things like Danny was saying, but the idea was to quantify how much age-related information is within the image. If we provide another input, it would tell us also, or it could probably rely on that information at all. We could also give the SAT fitting and everything, but that's not the point. The point is, how much is the environment contributing and can we tell?
But it's just that it's very fundamental that a factor of 2 in distance is a factor of 2 in size scale. And so
Yeah.
12 pixels doesn't mean the same thing.
Yeah.
True,
That's
true.
what it
But
is.
that's sort of the limiting, it's sort of the limiting, I mean,
No,
obvious,
it's fine. And so, but all we're saying is if you just put the distance in, you take that
we
problem out.
could take that off. Yeah, we can do a filtering based on the distance and then apply, yeah. Or, sorry, there's 2 more questions, right?
Yeah, so a practical question.
Okay.
You were given 2 options. One is to train a student, and the other one is to train your AI systems. Which would you do?
Well, if you train a student, you probably can ask and interact more, right? But if you train an AI, which I prefer?
For your research.
I always like to train the student so that student can train an AI pipeline for me.
That's a political answer.
I have a LensNet question. So
Yes.
why LSTM and not a transformer architecture? It
We
feels
could
like
have.
a very well-suited problem for the
Yes.
attention mechanism. But is there a difference in the interpretability work, or is it fine either way?
Great point. When you are talking about transformers, interpretability becomes much harder. You can look at tokens and embeddings. I'm having an interesting conversation here now, AI related. But you could aggregate embeddings in some way, see how much certain embeddings are activated, and you can still do explainable AI for transformers. It's a little harder because you don't have maybe a representation of what embedding, what does that embedding mean really. You don't have like a physical interpretation of it or things like that. It becomes a little more difficult. You can still apply the gradient. It's, the formulation. It's, in the end, it's an analytical formula. If you do the backpropagation with respect to the output, the input, you could still retrieve sort of that input contribution. But it becomes a little harder. For our purpose, we thought it was okay. We don't need to, make a huge model when there's already good performance with that. But yeah, that could be another student project as well. Yeah, thank you for the question.
All right, I think we are out of time, but if you have any more questions, Javier will be here for the rest of the day.
Thank you.